welcome to the UGC lecture series. This is a EPG Pathashala lecture series on the subject of computer science, and we are talking about the paper data structures. In this module, we are talking about the insertion and deletion of AVL trees. The last module we had already spoken about the properties of AVL trees. Remember, they are balanced binary search trees, and we have spoken about two operations that are normally done. One operation basically rotations, where we spoke about single rotation and double rotation. These operations were necessary to bring about balance when we do the insertion and deletion operations. So, in this module we are looking at the insertion and deletion operations and how we apply these rotations, which we spoke about in the last module with respect to AVL trees. So, these are the people responsible for the creation of this module, and these are the learning objectives of the module. First is to understand the insertion operations of AVL trees. So, we will not go too much into the detail of rotations, which we have already explained, but again we will do a little relook at that. Then we will discuss the deletion from AVL trees, and then we will also discuss in this module some of the pros and cons of AVL trees. So, the keywords are AVL trees, rotation, insertion, deletion, and most importantly rebalancing. Okay. So, let us look at insertion. So, remember, AVL tree is first and foremost a binary search tree. So, you do insertion using a binary search tree insertion algorithm. We are not going to discuss that. We have already seen how to do insertion into a binary search tree. Now, what we need is we want to rebalance the tree if an imbalance has occurred. That is what we want to do. And an imbalance occurs if a node's balance factor changes from either -1 to -2, because we are doing insertion, right, it cannot decrease. So, -1 to -2 or +1 to +2. So, if one of these two things happen, we know that an imbalance has occurred and we want to rebalance the tree. Okay. So, rebalancing is done, this is an important point, is done, we have discussed this slightly in the last module also, is done at the deepest or lowest unbalanced ancestor of the inserted node. So, see, remember that unbalance will actually be propagated up the tree, but what we do is we always do the rebalancing at the lowest or the deepest ancestor or the lowest unbalanced ancestor. We do not do it up the tree, we do it at the lowest point. Okay. Now, there are three insertion cases. One is that insertion does not cause imbalance at all, because we had 0, now it becomes +1, no imbalance, or it becomes -1, there is no imbalance. So, that is the first case. The second case is it is a left or right insertion that causes the imbalance. In this case it will be a single rotation, we will come to that. Actually, the rotations are 4 cases, we are talking about 3 cases as far as insertion is concerned. So, insertion causes no imbalance, insertion causes imbalance either in the left or right insertion only. And so, this requires a single rotation to rebalance, or on opposite sides, that is it is a left or right insertion, and this will cause an imbalance, in which case it requires a double rotation to do the rebalancing. So, this is the 3 cases of insertion, no balancing required, same side insertion or opposite side insertion, that is left right left, that is what we mean by opposite. So, these are the 3 cases. Now, let us look at the insertion algorithm. So, find the spot for the value, which is what we do in any BST algorithm, hang the new node, attach the new node, search back up. Now, you have to search back up looking for imbalance. Okay. Now, if there is an imbalance, then it could be an outside imbalance, that is where the insertion is on the same side, left right, that is also another term used for the same thing. It is not a new concept at all, this concept we have already discussed when we did single rotation. Now, again we have discussed when we did insertion left or right, then it is called outside. So, you perform single rotation and exist, or it is an inside type of imbalance, that is you have in the first case you have a right left, and the other case you have a left right, then you have to perform double rotation and exit. So, that is the insertion algorithm, spot for the value, attach the new node or hang the new node, search back to find the imbalance, and then look at whether it is an outside imbalance or an inside imbalance. So, now let us look at how insertion after insertion we do rotation in order to bring about the balance. That is what we are going to look at next. So, insert operation may cause balance factor to become 2 or minus 2 for some node. Remember, it is not if it is something that is the increase in left subtree, it becomes plus 2, increase in right subtree, it becomes minus 2. So, this is the insert operation. Now, only nodes on the path from this we have already discussed in the last module also. Only the nodes from the in the path from the root to the node that has been insertion point to the root node have possibly changed in height, because only there you have done the insertion. So, that is why we say after insertion we go up to the root node by node and we update the heights. Okay. Because of the insertion the heights have to be changed. So, we update it, and if a new balance factor, the difference is h left minus h right. Remember, we have discussed the properties of AVL trees where we said that the balance factor is the difference between h left and h right or h left minus h right is 2 or minus 2. We have to adjust the tree by rotation around that node, around the node. So, this is what we are going to talk about, the node, the root node. Now, there are 4 cases of insertion. Okay, 4 cases, what we are trying to say is 4 types of rotations. There we were talking about 4 cases of insertion, imbalance, single and double. Here we are talking about the 4 types, 2 singles, 2 doubles. So, 4 cases. Rebalancing is done at the deepest unbalanced ancestor of the inserted node. So, the node inserted node may not have an imbalance, inserted node will cause an imbalance to one of its ancestors. So, we want to find the deepest, that is the lowest level ancestor, and know that needs rebalance, let that node which has that problem be that ancestor be called x. The rebalancing is performed through 4 separate types of rotations, which we already saw in the last module. We are applying it here, that is all. So, the 4 cases are outside cases, that is requires only single rotation. Remember the term that we used, outside, that is left left, right right is called outside. So, insertion on the left subtree of left child. Please note, interestingly, when we say left subtree of left child, we are doing a right rotation, and right subtree of right child we are doing a left rotation, single left rotation. Then the inside cases which require double rotation. Here we have insertion into the right subtree of the left child of x, that x is the node from at which the imbalance has occurred. We call this as left right rotation, it is called left right, that is right subtree left child, right left right, and left insertion into the left subtree of right child of x we called as right left rotation. So, these are the 4 cases we have for insertion. Actually, it is similar for deletion, we will come to that later. So, single right rotation, single left rotation, right left rotation, right left. We have done all these rotations, we are now going to see how insertion. The only thing that we are doing is we are inserting a node using binary search tree, we are looking at it to see where the imbalance, so finding the deepest unbalanced node, and then we are doing the rotation as we discussed in the previous module. Let us consider a valid AVL tree, and let us see insertion of that x destroys the AVL property at node j. So, please note why we are talking about this is, if you take a valid AVL tree, insert x at that place. Now, insertion, the x does not have any imbalance, it is the node j that has the imbalance, and that is the node which is called the deepest ancestor here. Okay, so, this becomes h plus 1. So, that causes the node j to have a AVL property destroyed, because the height has become, I mean the balance has become 2. So, let us look at insertion into the left subtree of left child of x. This we will do using examples. So, here we have a tree. Remember, we are talking about an insertion into the left subtree of left child of x. So, insert 7. Now, when we insert 7, what happens? This is the 7 is inserted at that position, and what happens at this position here, and it is a left left insertion. Okay. So, now if you look at the balance factor at 9, the balance factor becomes minus 2, that is 1 minus of minus 1. So, that 1 minus of minus 1 which becomes minus 2. So, the balance factor at row 9 is what is violated, and node 9 is the deepest ancestor, unbalanced ancestor. That is what we are talking, that is a term used there. So, that is we have marked as x. Now, the first step is, okay, here it is, because it is same side, left child of left subtree, what we have to do is a right rotation. So, let us look at that. So, we have to do a single right rotation with 9 as the pivot, the unbalanced node as the pivot. So, we will do a rotation. The understanding of rotation is very easy, you just think the node is rotated. So, 9 becomes this side, 8 becomes the root and 7 becomes the left subchild, okay, 9 becomes the right. So, that is the issue. So, here we have the new node. If you can see 7, 8, 9 has, which was linear, has now been converted into a 7, 8, 9 this way, where V shape, where 7 is the left, 8 is the root and 9 is the child. So, now you have what is written there is not the balance factor, there is also the heights. Okay. What we are talking about here is now there is no imbalance. So, this is a single right rotation. Now, we look at insertion into the right subtree of the right child of x, okay, right subtree of right child of x. So, again we take an example, we insert 45, when we insert 45 it comes here. Now, you have a right, so you have to do a left rotation, again that linear path becomes a V. So, 40 becomes a root, 35 becomes a left child, 45 remains a right child. So, single left rotation, here 35 is the imbalance, where the imbalance occurs. So, please note those numbers are not balance factor, they are heights. So, you have 35 as x. So, your pivot is 35 and you do a single left rotation and you get this. Now, the tree is balanced. Please note 3 is not the balance factor, again it is a height. Okay. So, this is the that example of right. Now, we are done with single rotations. Now, let us go to the next example, insertion of left subtree of right child of x. So, this is a inside case. Okay. So, we have to do a right left rotation. So, let us take this tree and let us assume that we are inserting 34. Now, when we insert 34 it comes as a left child of 35, right. So, what you get is it comes as a left child of 35 and when it comes as a left child of 35 the imbalance is occurring at, please note there is a 45 there. So, the imbalance is occurring at 30, okay, the deepest unbalanced thing is occurring at 30. So, now you have 30 has a left child as left subtree as 40, in that 40 the right child is 35. So, that is why we call it as a left insertion into left subtree of right child of x, left subtree, that is where the insertion is occurring. So, the first step that you have to do, left subtree of right child of x, you have to do a right rotation. So, what you do, you take that 35 and you rotate it. So, rotate right with 35 as the pivotal. So, first we talk about the grandchild with 40 as the pivot, 35 about 40. So, what will happen? 35 becomes the root, 40 will become the child and you get this 34, 35, 40, 45, the change you see. Now, 30 is the x, remember. So, now you do a left rotate with 35, 30, 25. So, 30 comes as a child, rotate left 35 about the pivot 30, So, now you have this as a balanced tree. So, this is what is happening. Please note that 30, 40, 35, 35 has got the grandchild, okay, that is what the term we used before, grandchild. So, the grandchild is rotated about the parent which is the pivot, but that parent is a right child of the x, the deepest unbalanced ancestor. After we do that, then we do a rotation of 35, okay, about the x which is 30 and that is how we get first is a right, next is a left. Now, we do the mirror image case where we insert into the right subtree of the left child of x. So, let us take the example here and we do insert of 34. When we do insert of 34 here, what happens? When we do insert here, the imbalance, we do an insert of 7, at that point of time what happens? We do insert at 7, at that point of time what happens is 5 is the left child and we have inserted at 7 in the right subtree of the left child. So, the first operation, I mean the first rotation we have to do is a left rotation. So, we rotate with the grandchild. So, 6 is rotated about with pivot 5, we do a left rotation and we get this, if you see. Now, you have to take 6 and rotate it about 10, the new 6 and rotate it about 10, and that is a right rotate. So, we right rotate 6 about the pivot of 10 and we get the new tree. So, this is the new tree that we get, and this is the right subtree of left child rotation. Now, we talk about deletion. So, deleting a node x in an ordinary binary search tree, the last node deleted will be a leaf. Now, we have to trace the path from the new leaf towards the root, okay. And then for each node x encountered, check if the heights of left of x and right of x differ by at most 1. If yes, you proceed, and then if not, perform an appropriate rotation at x. Now, here the problem is every time you go up and you find an imbalanced node, you have to keep doing the rotation. There are 4 cases in the case of deletion. For deletion, there are 4 cases in the case of insertion, but for deletion, after we perform a rotation at x, we may have to perform a rotation as some ancestor of x also. Thus, we must continue to trace the path until we reach the root. So, this is the difference between insertion and deletion. Insertion, there are only 4 cases, but in the case of deletion, you first find x, the first deepest unbalanced node, and then you do a rotation. Then you have to keep on going until you reach the root and see whether there is imbalance. If there is imbalance, you have to continue doing the rotation. So, let us take an example. So, rebalance the tree if an imbalance occurs after deletion. There are 3 deletion cases: deletion that does not cause an imbalance, deletion that requires single rotation to rebalance, and deletion that requires 2 or more. It is not 2, because you may keep on doing the rotation. That is why we have a difference here, 2 or more rotations to rebalance. Okay. So, deletion with no imbalance, the current node P has balance factor equal. So, change the balance, shorter becomes false. So, there you have deleted. So, now it becomes no rotations are needed because the height has not changed. Now, let us assume here we want to delete 14. Now, if you delete 40, nothing, because the height is still 1, no change at all. So, there is no need of any rotation. Now, let us look at deletion with no imbalance. The balance factor of P is not equal and the taller subtree was shortened. So, the change of balance factor of P is equal. So, leave the shorter true. So, there are no rotations, and only thing is the height is reduced. There we did not have any height reduced. Now, we will go to the deletion with single rotation. Here the balance factor of Q is equal. If you look here, apply a single rotation, shorter becomes false. Okay. So, this is the idea of the height remains unchanged. So, here you are doing a single rotation left. There you have deleted, in T1 you have deleted. Note that T1's height is h minus 1, I mean after the deletion has occurred, and here you have h plus 1. Okay. So, there is a difference of there is an imbalance. So, what you will have to do is you have to change the height. So, what you have done is you have brought the T2 to the side and T3 remains as it is. The balance factor of Q is the same as that of P balance factor. Apply a single rotation and set the balance factor of P and Q to equal and leave the shorter as true. So, here the height has reduced. So, there are different methods at places at which you can apply. Now, let us take an example of deletion with single right rotation. So, here I am deleting the node 40. Now, when I delete the node 40, what happens? There is an imbalance at 35. So, I right rotate 32 about the pivot 35. So, single right rotation with 35 as pivot. So, I get this, and now I have a balanced node. So, this is deletion causing an imbalance. Okay. Please note what is again there is only the heights. Previously we discussed with respect to the heights, but here we are talking with respect to the imbalance. Now, let us look at an example of single left rotation. There we saw right. So, here we have a tree, we want to delete 32. Now, when we delete 32, there is an imbalance at 44. So, what happens? We do a rotation, left rotation. So, left rotation with 44 as the pivot, and this 62 comes there and 44 comes down. The whole tree has changed, but still it is only a single rotation. So, this is single left rotation. Now, we go with deletion with double rotation. The balance factor here of P and Q are opposite to each other. So, remember balance factor we are talking about here. So, apply a double rotation, set the balance factor of the new root to equal and leave the shorter one as true. So, this is height is reduced here. So, now we will look at an example of deletion with 2 or more rotations. So, here you have the tree. Now, let us assume we want to delete 40. Okay, when we delete 40, what happens? We have to do a right rotation about 35. By now, you should be familiar, this is a linear stretch and becoming a V. So, you do a right rotation with 35 as pivot, and now what happens? That part has changed, as you can see. Now, what happens? There is an imbalance at 30. Okay. So, you do a left again, I think right. So, you do a right rotation, because this right rotation with 30 as pivot. So, now 20 becomes the root and it becomes like this. So, right rotation with pivot as root. Here we have 2 rotations. Now, the pros and cons of AVL trees, it can be more than 2 rotations also, because sometimes at that point of time also you will have an imbalance. So, you have to go, normally if you have to go up to the root. In this case we went one node and then up to the root. So, it is double rotation, but actually it is not double rotation, it can be any number of rotations if the tree is big and there is an imbalance. So, you take the deepest unbalanced node, do a rotation, then you go up, see whether the imbalance continues, if so do again, then do again until you reach the root. So, deletion is different from insertion in that case. So, you have only 2 cases of rotation and then you repeated rotations depending upon where the imbalance is occurring. So, pros and cons of AVL trees, arguments for AVL trees for is search is of the order of log n, since AVL trees are always balanced, approximately balanced. Insertion deletion also of the order of log n. The height balancing adds no more than a constant factor to the speed of the insertion or deletion for that matter. Against AVL cases, difficult to program and debug, because you have to have more space to keep the balance factor, because you have to check the balance factor. Asymptotically faster, but rebalancing costs time. It is not that it does not, but on an average it is okay. Most large searches are done in database systems or disk and use other structures. It is not, they do not use AVL, major big ones. May be okay to have ON for single operation if total runtime for many consecutive operation is fast, for example, split trees. So, there are other alternatives to AVL trees. So, with this we finish AVL trees. So, AVL trees we spoke about the properties of approximate balance, then we spoke about rotations, then we applied that rotation when we were doing insertion and deletion. In insertion we had 4 cases, in deletion we have single rotation 2 cases, and then we have a number of rotations. It is not only double, it depends on how many steps we have to go up and reach the root. So, unless the root is also balanced, when you come across imbalance, you have to keep on doing the rotation. So, with that we finish with AVL trees. We continue with either binary balance search trees, balanced binary search trees in the next module. The summary of this course is, we explain the insertion operations of AVL trees, we discuss the deletion as I already told you, and we outline the advantages and disadvantages of AVL trees. Thank you.